Assalamu alaikum and welcome to our channel. I am Dr. Ismail. Today we will talk about the Gromacs tutorial Lysozyme in water. In this tutorial we will briefly explain how you can run Gromacs tutorial on Windows using Ubuntu WSL system. We will briefly explain the installation steps and we will explain in detail the demo of Lysozyme in water. So let's start. First of all, you need to go to Microsoft Store and in Microsoft Store type Ubuntu. It will give you multiple options of Ubuntu version. The most stable versions are Ubuntu 22 and Ubuntu 24. You can simply select anyone and click on the installation button like this one. Installation button and it will be installed. In this tutorial, I am using the Ubuntu 24 version. Once it is installed, it will show in your startup menu. You can type Ubuntu and it will appear. Just click on it. When you will run it on the first time, it will ask you to enter the password. You will enter the password and it will start running. Once you have set up the Ubuntu, you need to run these commands. First of all, you need to update your system. Copy this command and paste it into the Ubuntu terminal. It will ask you the password. Type the password you have saved and press enter. It will find if there is any updated packages, it will update it. So all the packages are updated and installed. Once you have installed these packages, the next step is installation of dependencies. Copy this command and paste into the Ubuntu terminal and run it. When this installation is finished, the next step is installation of Gromacs. For Gromacs installation, you need to copy all these commands and then run into the Ubuntu terminal. It will take some time depending upon your computer speed and it will complete. We have explained all these steps in detail in our previous videos. If you need to watch the step-by-step installation, you can watch our that relevant video. In this tutorial, we will only briefly explain. However, all these commands will be available in our YouTube tutorial description for your reference. You can simply copy paste and run the files. After compiling the Gromacs, you need to source. You need to run it every time when you run the Gromacs, because it is when you close the Ubuntu, it is detached. It is unlinked with your system. So copy this command and run it. So the source is activated. After the source is activated, there is another small app you need to install, which is Grace. We will use this app during our Gromacs tutorial to run the graphs and visual descriptions. So copy this command and paste into the Ubuntu terminal and press enter. It will start installing the program. When the installation is complete, it gives you the completion notice. Now we all set up for our Gromacs tutorial. Now we are going to run the Gromacs tutorial. This is the Gromacs tutorial. We are going to use it today. So here we click on the start tutorial. It gives you lot of information which is not necessarily to be followed. We will make it quick and we will make it easier and simple for you to run. We will make a confined command to run. We are using the same protein 1AKI1.pdb. You can download this command from the PDB structure. You can open this protein and download the legacy PDB format. Once this file is downloaded, copy this file and I have make a folder on the desktop with the name GMX. and I have pasted this file in that particular folder. The path of the folder can be seen here. It is C, user, HIBSA, desktop and GMX. So I need to access this folder from the Ubuntu. Simply copy your own path and modify this command according to it. You can see what is the difference. In this command there are the backward slashes. Replace all these backward slashes with the forward slashes. All the slashes with the forward slashes. This is the one change you are going to do. The second thing you need to change is remove the colon and make the C small. And the other thing you do, type C space forward slash space MNT forward slash. This means CD means it is going to entry and MNT is it is going to mount with your C drive and your folder. When the command is completed, copy this command, go to Ubuntu terminal and paste it and press enter. You can see now you are in the GMX folder. You can type dir and you can see here one aki.pdb file is present. Before going to the next step, open your protein to any viewer. Here I use the PyMol. I have opened the protein in the PyMol and here is the sequence menu. You can see here is the sequence, and what you need to do, you need to check if there any gap or missing residue present in it. If there is a missing gap in your protein, then the simulation will not run. You need to fill this gap with the proper complete sequence. The second important thing is these water molecules. The water molecule should not be present in your protein. You can remove water from here, or we will use the command to completely remove all the water molecule. So this is for visualization to have a quick idea about your protein. Then now we have checked our protein and we have made it sure that our protein don't have any missing residue. So the next step is the removal of water. Our protein name is 1aki.pdb. Okay, the protein name should be the same. So this is our protein name 1aki.pdb. If you cannot see the extension, go to these three dots, go to options, and here go to view, and in the view this is the option hide extension for file type. Uncheck it, apply it and press OK. You will see the extension. So we are going to remove the molecule. We are giving it that grep -v HOH means water 1aki.protein. This is our protein and the new name should be 1aki_clean.pdb. It will be the new name. If you want to change, you can change this name according to your own protein. What is your protein name? For this tutorial, I am going to run the same name. Simply copy this command and paste in Ubuntu terminal and press enter. And it is done. So the next step is generation of topology. For topology generation, we are using the GMX. GMX is for the Gromacs. PDB2GMX is the command or the package which used to generate the topology, and AKI clean.pdb is that file which we generated in the previous step, and it is free from water. And it will give it a new name which is known as 1aki_process.grow. If you want to change the name according to your protein, 1aki_process.grow. So we are going to copy this command and paste it in the Ubuntu terminal and press enter. It will give you some options. These are basically the force field. For this version, we are going to use OPLS dash AA /L. Type 15 and press enter. The topology is generated. So it will generate three new files. One is 1AKI underscore processed.grow file, which is basically the structure file. Then topol.top, which is your system topology, and pros.itp, which contain information about the restraint and position of heavy metal if present. We will need this file in the later steps. Now, our protein has been processed and it has produced three files. You can cross-verify from the folder. If you go to GMX folder, you can see here is the process, this is pros, and this is topol file. These files are generated. The next step is defining the box. We need to define a box in which the simulation will run. For this, we will use the command edit configuration and we will give it the path 1AKI process.grow, and the new one will 1AKI underscore new box. It will generate a new box with this diameter 1.0 and the structure will be the cubic. So to define the box, copy this command, go to Ubuntu terminal and paste it, press enter. That box has been generated. The box is generated. Now we want to fill this box with water molecule, with our solvent, because without water molecule it will not simulate properly. For this, we are going to use the Gromacs solvate command, and we are giving the new box file, which is 1AKI box, which we generated in the previous step. Now we are going to use it, and we are going to use the SPS 216 grow file, which is generated, and we are going to use the topol file for the topology information. Simply, you need to copy this file, go to the Ubuntu terminal and paste it and press enter, and it is done. Topology is generated. For the information, when Gromacs complete the command, it gives you a quotation at the end, which is a confirmation that your command has been run successfully. If we look into the tutorial, we have completed this first page, and then on the topology page we also completed this topology pages, and then the solvation step we also have completed the solvation phase, and then the adding on phase we also run this file. So now in the INS file we need to run this command. Sorry, not this command. We have to start from this command. We have copied this command here. This is using grom pp, and here we are using to 1KI solvation. This file was generated in the previous step here, and we are going to use the topol file and INTPR. Topol file was also previously generated, and next it will generate ins.tpr file. But to generate this file, we need another file which is with the name ins.mdp. We need to generate this file. ins.pb is basically the Python script which run the solvation step and generate the ins. You can find this file from the tutorial over here. If you right click on it, it will open a new page and it gives you a Python script. What you need to do, go to your folder in which all your commands are running. In the GMX folder which we have placed on the desktop, create a new text document, give it in a name ins.mdp. Make it sure like this one. Here is the extension .text. Make it sure when you change the name, this .text should also be changed. it should be mdp, ins.mdp. It will ask you to change the extension, say yes. It will give you this type of file. You can open this type of file with the notepad. Open with notepad. It is a blank one. You will go to this file which was generated from here, copy all its contents and paste it in the text folder. Click on Ctrl S and save all the content and close. What personally I like, you can see the icon is changed. I use Notepad++. It gives you a better visualization. The name should be ins.mdp. ins.mdp. For your suggestion, Notepad++. This is a short software you can install. It gives you a better visualization of the files working with it. So we have saved the ins.mdp over here. Now all the files are here. You need to copy this command, go to the Ubuntu terminal, paste it and press enter. Okay, it's giving an error that file ins.mb does not exist or not accessible. So need to change. Well, we need to find out what is the problem. Well, in our folder this is okay. There is a spelling mistake of the name. It's basically ins.mdp. Correct the spelling names, spells and save it. And now rerun the same command and press enter. Yes, it is done. You can note that if you make a spell mistake, the command will not complete it, it will not run. We have solvated our system. Now due to solvation, it will give it the charge. To make it neutral, we will add sodium or chloride in it to make all the system neutralized. So for neutralization, we will run this command, copy this command, go to the Ubuntu terminal and press enter. It is asking what group you want to choose. Here we will choose group number 13, which is SOL. Type 13 and press enter, and it is done. When the quotation come up, it means your job is completed successfully. You can see that all atom have been replaced with the chloride, means charge has been neutralized. Now our this step, solvation adding ion step, has been completed. The next step is energy minimization. For energy minimization, we need another script with the name minim and minim.mdp. You can copy this script. The name is minim.mdp. Copy its name. To avoid the spelling mistake, go to your folder, make a new text file, change the name, press yes, open it, copy complete content and paste it into the file. Press Ctrl S to save it and close it. So this script has been changed. Now this is the command which are we going to. This is our file which we have just provided. This is our solvated ions grow file which was generated previously. This is the topol file, and it will generate the energy minimization TPR, and the command is grompb. So copy this command, go to Ubuntu terminal and press copy, paste it and press enter, and it is done. After that, we are going to MD run for this energy minimization. Copy this command, go to Ubuntu terminal and paste it, press enter. So it is now running the energy minimization step. You can see I am using one MPI thread with 8 open threads and it is copying. So it will take some time according to your computer speed and it will complete it. When it will complete, you will go to the next step. Our job is completed. Energy minimization step has been completed. Now we want to see the result of energy minimization. For this, we are going to run this command which represent energy and potential.xvg, which means we want to see the potential energy. Copy this command, go to the Ubuntu terminal, paste the command, press enter. It will ask you the option about what you want to see the energy minimization. As I told earlier, we want to see the potential energy. Type 10, give the space and type 0. 0 means terminate, which means it is not going to do anything else. I repeat, type 10 space 0 and press enter. So it has given us the potential energy of this, error estimate of this, RMSD of this, and total difference of this. Now if you want to see the graph of this data, for this run the command xmgrace. Xmgrace is the small software we installed on the first step, and it will utilize the potential energy.xvg. This is the file which was generated in previous step. Copy this command, go to the Ubuntu terminal, paste the command and press enter. When you will press, it will pop up with a tool which is a grace tool. It will give you the idea of the potential energy, which means you can see with the passage of time the energy minimization is attained, which means the abrupt energy has been minimized with a steady flow. You can use it. The grace is a wonderful short tool which will be used for the visualization of your data. Close it after using it. Now we have completed this step of energy minimization. The next step is equilibration. In the equilibration stage, equilibration can be done at two steps, that NVT is constant number of particle volume and temperature, and NPT, which is constant pressure. To run this, we need another Python script which are provided over here. Right click on it, open it. This is basically the nvt.mdp. Same way, go to your GMX folder, create a new text file, give it the name nvt.mdp. Change it, yes. Open it, copy all the content, go to this file, paste this content and Ctrl S. Here one thing I want to show you, here at the line number 5 you can see the nano steps. It is show that this is 50,000 nanostep multiplied by 2, which becomes the 100 picosecond. You can use as much as you can. For this tutorial I am going to reduce it to save the time. I am going to change it. I am going to reduce 10 from all sides and it will become the 10 picosecond. Then press Ctrl S and save it. After saving it, close it, which means my calculation will be run on the 10 picosecond. So I have saved the file as nvt.mdp. After this I am going to run this command, which means it will use the grompp nvt.mdp, which we have saved. It will use the energy minimization.gro, which was produced during the previous command over here. Then it will use the topol and ultimately it will generate nvt.tpr. Copy this command, go to Ubuntu terminal, paste it and press enter. And it is completed. Then we are going to use the md run for NVT. Here that -p I have added it extra. Why I have added it? Because it will give you the time that when your command is going to complete. If you can see that in Gromacs tutorial they have not provided this command, but I will recommend you to add -b. Copy this command, go to the terminal, type, paste and press enter. So our command is started. You can see it is threads and 5000 steps and 10 picoseconds. The job is started. You can see it is giving me the time that it will complete in approximately 10 minutes. If I have not added -p, it will not show you the remaining time. So it is good to have an idea that when your command is going to finish. The job is completed. Now we run the energy of NVT of temperature. We want to see the temperature effect. Copy this command, go to Ubuntu terminal, paste the command and press enter. As we want to see the temperature, here the temperature is number 16. Type 16, give space, type 0 and press enter. It has generated the command. After it, this is temperature.xvg, then xmgrace temperature.xvg. Copy this command, go to terminal, paste and press enter. You can see the graph of temperature in the Grace software. Okay. If you like, you can go to file and also save the graph, or can save as you like. When you have visualized the graph, close it. Our step of equilibration using the NVT is completed. Now we are going to the second phase of equilibration, which is NPT. In a similar way, you can save the npt.mdpi from here. Right click on it, you will find the script. Go to your folder, create a new file, text file, give it the name npt.mdp. Press enter, open it, copy all the content and paste it in your file. In the similar way, at line number 5, I am again going to change it to 10 picosecond to save my time. You can use it to the 100 picosecond, even 1000 picosecond and so on. This is your choice. Just change it and save the file. After saving, close it. Once it is closed, then copy this command, which is npt.mdp. Rest of the information is saved. Copy this command and run it into the Ubuntu terminal. After completing, run the simulation using -v command, copy it and paste into the Ubuntu terminal, press enter. Again it is going to start about the 10 picosecond with 5000 steps. This is giving the time. It will take approximately 8 to 10 minutes for the 10 nanoseconds, 10 picoseconds. If you increase the picosecond, it will double, like it go to the 1 hour or like 8 minutes to 80 minutes or so on. To save the time, I just use the 10 picosecond for the demo. Now the job is completed. Now we want to see the effect of energy on the pressure. To check this, we will run this command in the Ubuntu terminal. After this, we will type 18 space type 0, press enter, because we are going to see the pressure. When we press the enter, it will generate the result for the pressure. To see the graph for pressure, we are going to use xmgrace pressure.xpg. This is the same file which we generated. We are going to see the graph from here. Copy this command and run into the Ubuntu terminal. The grace will use the graph of your pressure for this particular data. It is approximately 10 picosecond, the command which will be provided. Similarly, if we want to see the density, for density we have generated this command over here. Press density. This is the name you can give, density.xvg and so on. You can run all these one. If you see that density is present on the number 24, you can also use the volume, box size, enthalpy and so on. Type the relevant number, space, type 0, 0 is for the termination, and press enter. So it will give you the command for the run. And now to see the graph for density, type the specific xmgrace and type the name you have provided. Go to the Ubuntu terminal, type the command, press enter, and the grace will give you the visualization of that particular graph. Now you can see that we have already completed this second equilibrium stage. We also ran the pressure, we also gave the command for the density and so on. The next step is MD production. Now our protein has been energy minimized and we have equilibrated it with the NVT volume and NPT with the pressure. Now it is ready for the real molecular dynamics simulation. This is the real molecular dynamics simulation step. To run the MD simulation, here is the script. Open the script. This is the complete script. Same way, in your GMX folder, create a new text file with the name md.mdp. Open it. Copy all the content, paste in the folder and change the molecular dynamics simulation. It is 1 nanosecond. This is a big time. If you run on the CPU, it may take at least let's say in my system it will take approximately 8 hours. To save the time, I just reduce it from 1 nanosecond to 0.1 nanosecond, which means 100 picosecond. It will take approximately 1 hour or 1.5 hour to complete. You can run it on the 1 nanosecond, 10 nanosecond and 100 nanosecond. Normally journal publication require 100 nanosecond MD simulation to reach the better stability. But to demonstrate this demo, I am going to use only 0.1 nanosecond, which is equal to 100 picosecond. Save the file, close it. After closing it, this is our command which we are going to run. Grom-pp md.mdpi, which we just saved. npt.grow has been generated previously. npt.cpt is also generated. Topol.top is already present and it will generate the file with the name md0_1. You can change the name if you like. Simply, this is the configuration command. Go to Ubuntu terminal, paste the command and press enter. The topology has been saved. Now we are going to run the simulation again. Don't forget to add space -v. It will give you the real-time access that how much time it will take. Copy the command, paste the command and press enter. The job is going to start. For your ease, we will provide all the scripts file as well as the command file in our YouTube video tutorial. You can find in the description. You can find the link for downloading in the video description section. Now it is giving me the time that it will take approximately 1 hour to complete. If you want to utilize GPU, then run this command. This command at the end, that number of GPU present in your system, it will run faster and quickly. After the MD simulation, we will move toward the analysis. In this, the first step is centralize all the trajectories. To make it simple, we have separated out the command. The first command is trajectory, then we are using the MD file which is produced during our last run, and it will produce the axis file, and ultimately it will make it center to the all objectives according to the trajectories. Then we can calculate the RMSD and other values. If we look into our data, our simulation is almost completed. Approximately 1 minute is remaining. MD simulation is completed. Now we are going to run the analysis. First we will make it center as I discussed. Copy this command, paste it and press enter. It is now asking about what you want to do, which means which parameters you want to include in your analysis. You can use system, protein hydrogen bond, carbon alpha, backbone and so on. For this one, for centering purpose, I am going to choose one which is their protein, and for output I am going to use the system, which I will type 0 and press enter, and it is done. Now if I want to calculate the RMSD value of the protein or the backbone and so on, we will going to use this command. This command will run MD, that TPR, which was generated in our MD simulation, and we will name it as PBC, which was generated in the previous centralized file, and now we are using the same file over here, and now we are calculating the RMSD value in the nanoseconds. Copy this command, go to the Ubuntu terminal, paste it and press enter. I will select 4 at the both position, and the command is completed. Now next we are going to calculate the RMSD with relevant to the structure, crystal structure. For calculating this, we are going to run this command. This is for the crystal structure. We have changed the name. The initially simple RMSD value name was RMSD.xcg, while for the crystal structure we have changed the name RMSD_xtal.xcg. Now we are going to run this command. Copy this command, go to Ubuntu terminal, paste it, press enter. Again we are going to choose the group number 4, type 4, press enter. Then again type 4 and press enter. The crystal structure is already generated. Now if you want to see the simple RMSD value, use the XMGrace and copy this here. It's just like XMGrace space and copy RMSD.xvag. So I am going to copy this command and going to run it Ubuntu terminal. This is the RMSD graph of the simple RMSD values. Now close it. If I want to see the RMSD of crystal structure, I am going to run this command. This is for the crystal structure. It's depending upon your need what you want to do. Either you want to calculate for the simple RMSD or you want to calculate it for the crystal structure. The next step is the calculation of radius of gyration. For radius of gyration calculation, we are using the command gyrate for the same md.tpr, and we are saving it as gyrate.xvg. Simply we are going to run this command in Ubuntu terminal, and here we are going to choose the group number 1. Group number 1 is for the protein, so we are calculating the radius of gyration for protein type 1, and the job is completed. After this, run XM Grace and the name is guided.xvg. So xmgrace space guided.xvg. Copy this command, go to Ubuntu terminal and paste it. This is graph for the radius of gyration. You can see here this is the RG, radius of gyration, for the 100 picosecond, 0.1 nanosecond graph. In this way, you can calculate the radius of gyration and RMSD value for every group you want, like backbone, for carbon alpha chain, for main chain, hydrogen chain, side chain, water molecules, solvent molecules, ions molecule, ions and water, and so on. If you go into your working directory, you can see that here is the guided.xvg, rmsd.xvg, and xtl.xvg. You can open all these files in the Excel sheet. Open an empty Excel sheet, go to the file, click open, go to the browse. In the browse, go to the desktop. In desktop, I have saved a folder with the name GMX. In the GMX, type here all files. From here, select anyone, like I select rmsd.xvg. Then click on open. When open, a pop-up window will appear. Select on delimited, press next, then select the space, then press next and press finish. When you will finish, it will show you this data, and in this data you can see this is the value of backbone and their value. Select this column, go to insert, go to scatter chart, and then you can make a chart. So all the XVG values we have created, we can make graphs of our own choice. But don't forget to save this file. You need to save this file, save as, at the desktop, and with the name, change the value to Excel and RMSD. Save. Because this was temporarily open, if you don't save, it will disappear. If you close it now, you can see the file like here. This is RMSD file I just created. This is all about today. If you have any queries, you can write in the comment section. If you have not subscribed our channel yet, please subscribe and like. In upcoming video, we will cover all other Gromacs tutorial as well. Thank you so much for watching. Allah Hafiz.